Okay, so in this video we're going to look at calculus, and this first video we're going to see what is calculus. For me, calculus is the most amazing and exciting part of the whole junior Leaving Cert course. Okay, I think it's absolutely genius. So here we go. So if you look here, I have a graph, x and y axis. And this graph, I have drawn a curve on it. And the curve, the function of that curve, or the name of that curve, is fx equals x squared. Right? So what I mean by that is, if I put in 10 into this function, x squared, it will spit me out 100. And look, there's the 100. Okay? Right. Now, for argument's sake, I am going to say that this curve represents Usain Bolt's, I suppose, 100-meter sprint race. Okay, so what I mean by that is, after 6 seconds, he's after travelling 25 meters. After 9 seconds, he's after travelling 75 meters. After 3 seconds, he's after travelling about 10 meters. Okay? If we look at the curve then, and if I was to ask you the question, when do you think he's going faster? At the start of the race or the end? Okay, think about a race, right? The gun goes and off he goes. He's going to be going slow at the start of the race, isn't he? He's going to be starting to pick up speed. By the end of the race, he's going to be at his quickest. And look at the curve. The curve starts out fairly flat, but by the end of the race, it's pretty steep. Okay, look at the slope of the curve there, whereas look at the slope of it there. Okay, so by that logic, we can say, and we would have looked at that in functions anyway, but the steeper the curve, the quicker the speed. Okay, so just keep that in mind. The steeper this curve, the quicker the speed. Right? Okay, so what I'm going to do here is I'm going to get Usain Bolt's average speed over the whole race. Okay, and for argument's sake, let's just say he ran the 100 meters in 10 seconds. I know in reality he ran it, I think it was 9.4 something seconds or 9.7 something seconds, but for argument's sake we're going to say he ran the 100 meters in 10 seconds. So let's get his average speed. Okay, well, the average speed will be from the start of the race to the end. So if I put a point at the start of the race to the end, if I join those two with a straight line, that I suppose line, well, the slope of that line will be, the slope of the line will equal his speed. Just keep that in mind. The slope of the line will equal his speed. Okay, but park that for a minute. Right, let's look at this. We want to find his speed. Speed is distance over time. Okay, so from the start of the race, so from here, he travelled for 10 seconds, so the time is 10. So from here all the way to here is 10 seconds. And he travelled a length of 100 meters. So from here, 0, up to 100 meters. So the distance is 100 meters. And 100 divided by 10 is 10 meters per second. So that's his speed, right, for the whole race. However, what if I just wanted to find out his speed for the second half of the race? So we'll say from here, so 5 to 10. Let's do it again. So his average speed for the second half of the race. Well, this will give me here and then this here. Right. So again, speed is distance over time. So the time he took, well, from 5 seconds to 10 seconds will be 5 seconds. And then here, the distance he travelled here is 25 seconds. So from 25 meters. So from 25 meters up to 10 meters is 25 meters, 100 meters minus 25 meters is 75. And if we divide 75 by 5, we will get 15 meters per second. Okay? So the second half of the race, his average speed was 15 meters per second. We'll do one more. We'll say the last 2 seconds of the race. So from here to here, how fast was he going? Right, the time he travelled was from 8 seconds to 10 seconds, which is 2 seconds. And 8 squared will give us 64. Should be kind of here, I guess. Okay, 64. If my graph was better, it would match, but let's just say up here to 64. And so the distance he travelled was from 64 meters to 100 meters, which would be 36 meters. So in 2 seconds, so for the last 2 seconds of the race, he travelled 36 meters, which will give us 18 meters per second. Okay? Right. You might have noticed something there. When I was doing this distance over time, this distance over time was actually the same as the rise over the run, when you think about it. I'll do it again. This time I'll use rise over run. So from here to here, this is the whole race. Right? From here to here is 10 seconds. Okay, but it's also a run of 10. And then from here to here, or from here to here, is 100, which is a rise of 100, which is 10 meters per second. And that's the exact same. If I do it this way, the rise over run, or if I do it this way, the distance over time, it works out the exact same. Which proves really that the slope of that line, okay, from here to here, or if I was doing from 8 seconds to 10 seconds, which would be the slope of the curve from here to here, or if I wanted his average speed from the second half of the race, so 5 seconds, here would be the slope of the curve from here to here. Okay, so if you remember, the second half of the race, I think it was 15 meters per second. So that means the slope of this line from here to here is 15. And we did also the last 2 seconds of the race. So the slope of the curve from here to here is 18. So we are after proving that the slope of a curve equals the average speed. Okay. But that's giving me average speed. That's giving me average speed between so many seconds, between the second of the race and the 10th second of the race, or the last 2 seconds of the race. What if I didn't want to find the average speed of Usain Bolt over 2 seconds or over the last 5 seconds of the race, but I wanted to find his speed at an exact point. So I want to find his exact speed, bang, at 5 seconds. Okay? Not his average speed between 10 seconds, or between 5 and 10 seconds, but his actual speed, that instantaneous speed at 5 seconds. Well, I suppose one thing we could do, we could look and we could say, well, do you know what? Actually, just rewind there. If I could find, there's my point that I want to find his actual speed at. Now, if I could find the slope of that curve at that point, So the slope of the curve at that point is something like this. If I could find that slope, that would be his speed. However, in order to find the slope of a line, we need 2 points. And in this I only have 1. In all the other ones, when I was finding his average speed, I had 2 points. But for this question, his actual speed at that exact point, I have only 1 point. So what could we do? Well, one thing we could do is we could say, well, do you know what? If I got his average speed between here and here, that might be close enough to it. Then someone else might come along and say, yeah, that's fair enough, but you know what? You'd be more accurate if you got it between here and here, because the slope of that curve would be closer to the actual curve at that point. Someone else might come along then and say, well, actually, lads, if we got the slope of the curve between 6 seconds and 4 seconds, that'll be pretty close to his actual exact speed at 5 seconds. And then someone else might come along and say, well, no, lads, what if we got his average speed between 5.5 seconds and 4.5 seconds? That would be closer. And likewise, again, someone else could come along and say, well, actually, could we get his average speed between 4.99 seconds and 5.01 seconds? Wouldn't that be very close to his actual speed at 5 seconds? And the answer is yes, it would, but it would never give us his exact actual speed. In calculus, we will come up with a way of finding out what his exact speed is there. Or another way of saying it, we will come up with a way of finding the exact slope of that tangent to that curve at that exact point. Okay, that's calculus. Okay, the next video we'll show you how.